Okay, let's talk about imaginary numbers. Imaginary has got to be the worst branding in the history of math, because these numbers and the world of complex analysis they open up are anything but imaginary. In fact, they're one of the most powerful, practical tools ever invented. So today, we're going to take a visual journey to see what's really going on.
So it all kicks off with this one simple question. We're all used to thinking of numbers laid out on a straight line, right? Stretching out to infinity in both directions. But what if that wasn't the whole story? What if numbers could break free from that one dimension and move up and down too?
And that question leads us right here to our first stop, going beyond the number line. To really get a feel for this new two-dimensional world, we're going to need a new map. One that's a whole lot bigger than that single line we all learned about in school.
Yeah, on the left, that's the stuff we all know, right? The real number line. Familiar territory. But on the right, well, that's our new playground, the complex plane. We still got our classic left-to-right real axis, but now we've added a whole new direction, a vertical imaginary axis. Every single point on this grid is now its own number.
So, how do we actually write down an address for some point on this new map? Well, we use what's called a complex number. It looks like this: z equals x plus iy. The x just tells you how far to go left or right, and the y tells you how far to go up or down. It's really just a coordinate system, but the cool part is that it treats that whole point as one single number. And at first, the simple stuff works exactly like you'd hope it would. Adding two complex numbers is basically just like adding two arrows together. You're just shifting a point from one place to another. So far, so good, right? But this is where things start to get a little weird.
With real numbers, it's easy. We can always say 1 is bigger or smaller than another. 5 is bigger than 1. Simple. But in the complex plane, that whole idea just falls apart. Look at the number I, sitting up there on the vertical axis. Is it bigger than 1? Is it smaller? The question doesn't even make sense. It's like asking if north is bigger than east. This is our first big clue that we're not in Kansas anymore. The rules here are just different.
Okay, so if bigger or smaller is off the table, what can we say about these numbers? We need a new way to describe them. And we do that with two key ideas, both of them geometric. First, the modulus. That's just a fancy word for its distance from the center, its length. And second, the argument. That's its direction or its angle.
Now this is where we really start to shift our thinking. Instead of thinking in terms of how far left/right and how far up/down, we start thinking in polar coordinates. We think how far from the center and in what direction. Every number now has a length, we'll call it r, and an angle, theta. And trust me, this perspective is the key that unlocks all the magic.
All right, let's get into the geometry of multiplication, because honestly, this is where complex numbers stop being just a neat trick and become something really special. We're about to see that multiplication in this world isn't just some abstract calculation. It's a physical action, a rotation and a scaling that you can literally see.
Now, if you try to multiply complex numbers using that x plus iy form, the algebra gets kind of messy. But if you use their polar form, their length and angle, it becomes incredibly elegant. Yeah, I know, this equation might look a little intense with the e and the I, but ignore the symbols for a second. The real magic isn't in the equation itself, it's in the beautiful, simple action it describes.
So here's the deal, boiled down to two simple steps. When you multiply two complex numbers, you just multiply their lengths and add their angles. That's it. It's not just algebra, it's a physical transformation. You stretch it and you turn it.
Let's make this totally concrete. Think about the number I itself. Where is it on our map? It's 1 unit straight up. So its length is 1, and its angle is 90 degrees. So if we multiply any number by I, what happens? Well, according to our rule, we multiply its length by 1. So no change there, and we add 90 degrees to its angle. Multiplying by I is a pure 90-degree turn to the left. That's what I really is.
All right, so we're starting to get the lay of the land in this new world. We know how to move around. So what's next? Well, let's try to figure out the laws of physics here. Let's talk calculus. And that brings us to a stricter kind of calculus.
And right away, we hit a huge question. See, back in regular calculus, you're on a line. You can only come at a point from the left or the right. Easy. But here, in this big open plane, you can approach a point from literally any direction you want. From above, from below, from some weird diagonal angle. It's a free-for-all.
So, for a derivative to even make sense here, We have to lay down a really tough rule. The answer you get has to be the exact same no matter what path you take to get there. The result you get from sliding in from the side has to be the exact same as the result you get dropping in from above. No exceptions.
And when you force that one rule to be true, these equations just pop right out. They're called the Cauchy-Riemann equations. And yeah, they look a bit technical, but what they really are is a mathematical straitjacket. They lock the real and imaginary parts of a function together in this incredibly rigid, interconnected way.
Which really begs the question, right? This seems crazy restrictive. Why would anyone want to work with a system where most of the functions you can think of are just not allowed? Why would you willingly put on this mathematical straitjacket?
Well, let's get to the payoff. Because the reason we put on that straitjacket, the reason we accept all these incredibly strict rules, is because it gives us a genuine superpower. It's time to talk about the integration superpower.
That's the answer. All that strictness, all those rules, they aren't a limitation. They are the source of the magic.
And the first taste of that magic is Cauchy's integral theorem. All it says is that for any function that plays by our strict derivative rules, the technical term is holomorphic, if you take a walk in any closed loop and add up the function's value every step of the way, when you get back to where you started, the grand total is always 0. Exactly 0. It's a perfect conservation law.
But this is the star of the show, Cauchy's integral formula. I know it looks like just another messy equation, but I promise you what it says is one of the most mind-blowing, beautiful things in all of mathematics.
So what does this magic formula actually do? It says that if you know what a function is doing just on the edge of a region, say on the perimeter of a circle, you automatically know its exact value at any single point on the inside. All of it. Think about that. It's like knowing the temperature on the walls of a room and being able to perfectly calculate the temperature at the very center. It's a mathematical crystal ball. This is the superpower we were promised.
And this isn't just some cool math puzzle. This is the secret weapon for engineers and physicists. This crystal ball property lets them solve ridiculously hard problems involving things like airflow over a wing or the flow of electricity by transforming a messy, real-world shape into a simple one where they already know the answers. So we're left with this incredible, almost holographic idea that for these special functions, the information for the entire inside is somehow painted on the edge. It really makes you wonder, doesn't it? What other deep, hidden connections are just waiting for us to find them in this strange and beautiful world of numbers?